In the quiet reaches of our solar system, beyond the orbits of the giant planets, beyond the familiar glow of Saturn's rings and Neptune's distant blue sphere, there exists a realm we once knew only through mathematics and speculation. For decades, this outer frontier remained hidden in shadow, a place where sunlight arrives as little more than a whisper, where temperatures descend to depths we can barely comprehend. This is the domain of Pluto and the Kuiper Belt, a region that holds secrets about the earliest days of our cosmic neighborhood. And in the summer of 2015, after nearly a decade of silent travel through the darkness, a small spacecraft arrived to show us what had been waiting there all along. What it found was not a barren, lifeless world, but something far more beautiful and strange than anyone had imagined. This is the story of that journey and the quiet wonders it revealed. Let yourself drift now into the stillness of deep space, where every discovery unfolds slowly, gently, like morning light spreading across a frozen plain. There is no urgency here, only the patient unfolding of cosmic beauty. Close your eyes and let the story carry you outward, beyond the familiar, into the soft darkness where Pluto waits. Before we journey to Pluto itself, we must understand what this distant world meant to us for so long. Discovered in 1930 by a young astronomer named Clyde Tombaugh, Pluto entered our awareness as a tiny point of light moving slowly against the backdrop of stars. For 76 years, it held the title of the ninth planet, the final sentinel at the edge of the known solar system. Yet in all that time, Pluto remained fundamentally mysterious. Even our most powerful telescopes could resolve it only as a blurred disk, a smudge of light that refused to come into focus. We knew it was small, perhaps smaller than Earth's moon. We suspected it had a companion, a moon we would come to call Charon, locked in a gravitational dance. But the true nature of Pluto's surface, its geology, its atmosphere, all of this remained hidden behind the veil of distance. Astronomers created maps based on subtle changes in brightness as Pluto rotated, but these were abstract reconstructions, educated guesses built on fragments of data. The world itself remained unseen, and so Pluto became a symbol of the unknown, a reminder of how much remained beyond our reach, waiting patiently in the cold and dark. As the 20th century drew to a close, scientists began to advocate for a mission to this distant world. They understood that Pluto was not simply a curiosity, but a key to understanding the solar system's formation. Out there in the cold, far from the sun's warmth, materials had been preserved in their original state, frozen in time like insects in amber. To visit Pluto would be to glimpse the solar system as it was billions of years ago, when everything was new and the planets were still finding their places. But sending a spacecraft to Pluto posed extraordinary challenges. The distance alone was staggering, more than 3 billion miles at its closest approach. A conventional trajectory would take decades, and time was of the essence because Pluto's tenuous atmosphere was slowly freezing and falling to the surface as the dwarf planet moved farther from the Sun in its elongated orbit. The spacecraft would need to be fast, light, and equipped with instruments capable of capturing data during a brief flyby lasting only hours. In 2001, NASA approved the mission. They called it New Horizons. And on a cold January morning in 2006, the spacecraft lifted off from Cape Canaveral, beginning the longest journey ever undertaken to explore a single world. New Horizons was built for speed. It left Earth traveling faster than any spacecraft before it, moving at over 36,000 miles per hour. Even at this velocity, the journey to Pluto would take 9.5 years. Think of that span of time. Nearly a decade of silent flight through the void, with no possibility of return, no chance to repair or adjust beyond the commands sent from Earth at the speed of light. The spacecraft was alone in a way few machines have ever been. For the first year, New Horizons crossed the orbit of Mars, then passed through the asteroid belt without incident. In February 2007, It reached Jupiter, using the giant planet's gravity to slingshot itself even faster toward the outer solar system. As it swung past Jupiter's swirling clouds, it captured images of volcanic eruptions on the moon Io and observed the complex dynamics of Jupiter's atmosphere. But this was merely a preview, a technical rehearsal. Jupiter was known territory. Pluto was not. After the Jupiter encounter, New Horizons entered what mission controllers called hibernation mode. To conserve power and reduce wear on its systems, the spacecraft essentially went to sleep, waking only briefly each year for systems checks. And so it continued year after year, crossing the orbits of Saturn, Uranus, Neptune, moving ever deeper into the outer darkness, toward a world no one had ever seen. During those long years of flight, our understanding of Pluto's place in the cosmos shifted. In 2006, just months after New Horizons launched, the International Astronomical Union redefined what it meant to be a planet. According to the new criteria, Pluto did not qualify. It had not cleared its orbital neighborhood of other objects. Instead, it was reclassified as a dwarf planet, one member of a much larger population of icy bodies orbiting in the Kuiper Belt. The decision was controversial and sparked passionate debate. Some felt that Pluto's demotion diminished its importance. Others argued that the new classification actually elevated Pluto's significance, revealing it not as an oddity but as the first discovered example of an entirely new category of solar system objects. For New Horizons, the debate was irrelevant. The spacecraft did not care what we called Pluto. It simply continued on its trajectory, crossing invisible boundaries in the silence of space. And perhaps this is the deeper truth, that names and categories are human constructs, while the worlds themselves exist in their own right, indifferent to our classifications, waiting to reveal their secrets to anyone patient enough to make the journey. Pluto remained Pluto, whatever we chose to call it, and it was still waiting. As 2015 began, New Horizons finally emerged from hibernation for the last time. The spacecraft was now in the final approach phase, closing in on Pluto at thousands of miles per hour. On Earth, the mission team prepared for the encounter with a mixture of excitement and anxiety. They had worked for years to reach this moment, but the flyby itself would be over in a matter of hours. There would be no second chances. If anything went wrong, if the spacecraft malfunctioned or if it collided with unseen debris, the entire mission would end in silence. The team had done everything they could to ensure success, but the final outcome rested with the spacecraft itself, now too far away for real-time control. Commands sent from Earth took over 4 hours to reach New Horizons, and another 4 hours for any response to return. By the time Mission Control learned that the spacecraft had reached Pluto, the encounter would already be over. In January, when Pluto was still just a distant point of light, New Horizons began taking images. At first, these showed nothing more than Hubble had revealed, but as the weeks passed and the spacecraft drew closer, the images began to change. Slowly, pixel by pixel, Pluto began to resolve. It was no longer a point of light or a blurred disk. It was becoming a world. By April, the images showed clear surface features, light and dark regions that hinted at complex geology. The mission team watched in fascination as a bright, heart-shaped region emerged on Pluto's surface, its outline becoming clearer with each passing week. They had expected Pluto to be heavily cratered, a dead world frozen in time, its surface recording billions of years of impacts. But the emerging features suggested something different. There were smooth areas, regions that appeared to have been resurfaced relatively recently in geological terms. This implied activity, processes that had modified Pluto's surface within the last 100 million years or so. But what could drive such activity on a world so cold and distant? The mystery deepened as New Horizons drew closer. In June, the spacecraft was close enough to begin resolving features as small as a few miles across. The bright, heart-shaped region dominated the visible hemisphere. Dark, reddish regions appeared near the equator, and at the North Pole, a dark cap suggested seasonal processes at work, materials that changed with Pluto's long seasons. Each new image brought more questions. Pluto was refusing to fit into simple categories. It was complex, dynamic, and utterly unexpected. The spacecraft pressed on, closing the final distance. On July 14, 2015, New Horizons reached its closest approach to Pluto, passing just 7,800 miles above the surface at over 30,000 miles per hour. For a few hours, the spacecraft worked continuously, its instruments capturing images, measuring temperatures, analyzing the tenuous atmosphere, mapping surface composition. Every sensor was active, gathering data as quickly as possible before Pluto receded into the distance once more. Then, as planned, New Horizons turned its antenna away from Earth and focused entirely on its observations. For the mission team, this was the most anxious period. The spacecraft was out of contact, executing its program sequence with no ability to receive new commands or report problems. If anything went wrong, they would not know until it was too late. The hours passed slowly. Back on Earth, mission control waited. Finally, as night fell over the United States, the appointed time arrived. New Horizons reoriented itself, pointing its antenna back toward Earth. A signal began the long journey home, crossing 3 billion miles at the speed of light. When it arrived, over 4 hours later, it carried a simple message. The flyby had been a success. The spacecraft was healthy, and it had seen wonders. Now began the slow process of transmitting the data home, a process that would take over a year to complete. But the first images arrived within days, and they changed everything. The first detailed image of Pluto appeared on the world screens in the early morning hours of July 15th. Even the mission team, who had watched Pluto slowly come into focus over the preceding months, were stunned by what they saw. The bright heart-shaped region, now named Tombaugh Regio in honor of Pluto's discoverer, dominated the view. But it was the texture and variety of the surface that astonished everyone. This was not a dead, crater-pocked ball of ice. This was a world with mountains, plains, and features unlike anything seen elsewhere in the solar system. To the west of the heart, dark regions showed subtle textures, possibly ancient cratered terrain. But within the heart itself, particularly in its western lobe, which would come to be called Sputnik Planitia, the surface was extraordinarily smooth and young. There were almost no impact craters, suggesting that this region had been resurfaced within the last 10 million years, a blink of an eye in geological time. And there were patterns in the ice, cellular structures hundreds of miles across, outlined by shallow troughs. What could have created such features? The answer would emerge slowly as scientists studied the data and ran computer simulations. But even in those first images, it was clear that Pluto was geologically active, a living world in its own way. As higher resolution images arrived in the following days and weeks, the full majesty of Pluto's landscape came into view. Near the western edge of Tombaugh Regio, a mountain range rose from the frozen plains, peaks reaching over 2 miles high. These were mountains made of water ice, which at Pluto's temperatures behaves like rock, forming solid, durable structures that can support significant relief. The existence of these mountains was itself remarkable. On such a small world, internal heat should have dissipated billions of years ago, leaving the interior frozen solid. Mountains require a solid foundation to support their weight. The fact that these peaks existed suggested that Pluto's water ice crust was thick and strong, not soft or slushy. But what about the smooth plains of Sputnik Planitia? These showed a completely different character. The surface there appeared to be nitrogen ice, softer and more mobile than water ice at the same temperature. And the cellular patterns suggested convection, a process where warmer material rises from below while cooler material sinks. This is the same process that creates the patterns you see in a pot of slowly boiling water. But on Pluto, it was happening in nitrogen ice at temperatures near absolute zero. The cells were enormous, some hundreds of miles across, each one taking perhaps 500,000 years to complete one convective cycle. Time moved slowly here, but it moved nonetheless. The beauty of Sputnik Planitia lies not in dramatic features, but in its serene, quiet geometry. From high above, the cellular patterns create a mosaic of slightly different shades, brighter regions and slightly darker troughs where material is descending. There is a sense of order here, of natural processes working with mathematical precision to organize the surface. At the boundaries between cells, where descending material meets, there are sometimes small accumulations of darker material, possibly organic compounds or other impurities that have been concentrated by the convective flow. These form delicate tracings, like veins in marble or cracks in porcelain. Along the eastern edge of Sputnik Planitia, where the smooth plains meet the rougher, darker terrain of eastern Tombaugh Regio, there are features that resemble glaciers. These are flows of nitrogen ice moving slowly from the plains into the valleys and depressions of the surrounding highlands. The flow is so slow that you could watch for a human lifetime and see no change, but over thousands of years, the ice advances, fills the valleys, and then perhaps retreats again when conditions change. This is a world where seasons last for decades, where ice comes and goes on timescales that dwarf human civilization. Yet the patterns are there to read if you know how to look. Scientists studying these glacial features realized that they were witnessing a kind of ice cycle on Pluto, similar in some ways to the water cycle on Earth, but operating with nitrogen instead. Pluto's atmosphere, though incredibly thin, contains nitrogen gas that has sublimated from the surface ice. As Pluto moves in its elliptical orbit around the Sun, the amount of sunlight reaching different parts of the surface changes. When a region is warmed, nitrogen ice sublimates into gas, thickening the atmosphere slightly. When that gas drifts to colder regions or when Pluto moves farther from the Sun in its orbit, the nitrogen condenses and falls back to the surface as frost or snow. Over time, this process can transport significant amounts of nitrogen ice from one region to another. Sputnik Planitia appears to be a cold trap, a low-lying basin where nitrogen ice accumulates over time. The weight of all this ice has actually caused the basin to sink slightly, creating a positive feedback loop. As more ice accumulates, the basin becomes deeper and colder, attracting even more ice. This process may have been going on for millions of years, slowly concentrating nitrogen ice in this one location while depleting it from other parts of Pluto. It is a slow, patient reshaping of a world, driven by nothing more than temperature differences and the basic physics of sublimation and condensation. The colors of Pluto are subtle but significant. At first glance, the world appears to be dominated by whites, grays, and tans. But when the colors are enhanced to make subtle differences more visible, a remarkable palette emerges. The nitrogen ice of Sputnik Planitia is relatively white, almost pure in its reflectivity. But many other regions of Pluto are distinctly reddish, particularly near the equator and in the darker terrains that border Tombaugh Regio. These red hues are created by organic compounds called tholins, which form when ultraviolet light from the sun and energetic particles from space interact with methane and nitrogen in Pluto's atmosphere. The chemical reactions are slow and occur primarily in the upper atmosphere, where the molecules are most exposed to radiation. The tholins that form are complex hydrocarbons, long chains of carbon and hydrogen with nitrogen mixed in. They are not alive, but they are organic in the chemical sense, and they are the same class of compounds that may have been important for the origin of life on Earth billions of years ago. On Pluto, these tholins gradually settle out of the atmosphere and accumulate on the surface, giving it a reddish-brown tint. Over millions of years, exposed surfaces become darker and redder, creating a visual record of age and atmospheric chemistry. In enhanced color images, some regions of Pluto appear almost burgundy, a deep red-brown that speaks to long exposure and heavy tholin accumulation. Other areas, particularly in the far north, show a more neutral gray, possibly indicating water ice or other materials that resist the reddening process. And then there are the strange yellow tones visible in some regions, hints of sulfur or other compounds mixed into the surface ice. The overall effect is painterly, a landscape that seems to have been composed with an artist's eye for subtle color relationships. But these are not artistic choices. They are the inevitable result of chemistry and geology working together over vast spans of time. Each color tells a story. Each shade represents a different process or a different age. To look at Pluto's surface in color is to read a complex history written in ice and organic molecules, a history that extends back to the earliest days of the solar system. The beauty here is not decorative. It is informational, a visual language that scientists are only beginning to learn to read. And every image reveals new sentences in this ancient text, new clues to understanding how this world came to be and how it continues to change. Pluto's atmosphere, though tenuous almost beyond imagining, plays a crucial role in shaping the world's appearance and behavior. At the surface, the atmospheric pressure is roughly 100,000 times lower than Earth's atmosphere at sea level. If you stood on Pluto's surface, you would effectively be in a vacuum from a human perspective. And yet this trace atmosphere is substantial enough to support weather, to transport material from one place to another, and to create optical phenomena visible from space. New Horizons detected multiple layers of haze in Pluto's atmosphere, extending up to over 100 miles above the surface. These haze layers are made of tiny particles, likely tholins and other organic compounds that have condensed from the gas phase. They form in distinct bands, possibly related to temperature inversions and atmospheric waves. When New Horizons looked back at Pluto after the flyby, with the sun behind the dwarf planet from the spacecraft's perspective, these haze layers became visible in exquisite detail. They appeared as delicate blue rings surrounding Pluto's dark silhouette, layers of aerosol particles scattering sunlight in a phenomenon similar to the blue sky of Earth. The blue color indicates that the particles are very small, comparable in size to the wavelength of visible light. This is Pluto's version of a sky, not something you could see from the surface, but visible nonetheless from the right vantage point. The structure of these haze layers suggests that Pluto's atmosphere is more complex and dynamic than its thinness might suggest. There appear to be winds, circulation patterns, and possibly even clouds, though these would be made of nitrogen ice crystals rather than water droplets. The temperature structure of the atmosphere is also unusual. Near the surface, the temperature is around -375 degrees Fahrenheit, cold enough to freeze almost any substance. But in the upper atmosphere, temperatures actually increase, creating an inversion layer. This is partly due to heating from solar ultraviolet radiation and partly due to the cooling effect of molecular emission at lower altitudes. The result is an atmosphere that is stable in the vertical direction, resisting mixing and convection. This stability allows the haze layers to persist and remain distinct rather than being stirred together into a uniform fog. As Pluto moves through its 248-year orbit around the Sun, the amount of sunlight it receives varies dramatically. At perihelion, its closest approach to the Sun, Pluto receives about 3 times as much sunlight as at aphelion, its farthest point. This variation drives long-term changes in the atmosphere. When Pluto is closer to the Sun, more nitrogen sublimates from the surface, thickening the atmosphere. As it moves away, the atmosphere gradually freezes and collapses, returning to the surface as frost. New Horizons arrived when Pluto was moving away from the Sun, but the atmosphere was still relatively robust. In another few decades, it may be significantly thinner. One of the great surprises of the New Horizons mission was the realization that Pluto might harbor a subsurface ocean of liquid water beneath its frozen crust. This possibility emerged not from direct detection, but from careful analysis of Pluto's geology and gravitational field. The key evidence came from Sputnik Planitia itself. This smooth basin sits directly on Pluto's equator, almost exactly opposite to Charon in the sky. This positioning is unlikely to be a coincidence. Tidal forces between Pluto and Charon tend to organize material along and perpendicular to the line connecting the two bodies. For Sputnik Planitia to be where it is, it must represent a mass concentration, a region where the density is slightly higher than the surrounding terrain. But the basin appears to be filled with nitrogen ice, which is less dense than water ice. So how can the basin be a mass concentration? The answer requires the presence of something denser beneath the nitrogen ice. Computer models suggest that a layer of liquid water, perhaps mixed with ammonia to lower its freezing point, could exist beneath the basin. This subsurface ocean would be denser than the overlying ice shell, creating the necessary mass concentration. The liquid layer might be tens of miles deep, sandwiched between the nitrogen ice above and the rocky core below. If this ocean exists, it has been there for a very long time, kept liquid by heat from radioactive decay in Pluto's core, and possibly by the insulating effect of the thick ice shell above. The implications of a subsurface ocean on Pluto are profound, though we must be careful not to overstate them. Liquid water is a prerequisite for life as we know it, but it is far from sufficient. Pluto's ocean, if it exists, would be completely isolated from sunlight and from the organic chemistry happening in the atmosphere and on the surface. It would be dark, cold, and likely highly saline or contaminated with ammonia. Whether such an environment could support any kind of biochemistry is unknown. But the mere possibility reframes how we think about Pluto. It is not simply a frozen relic, a dead world preserved from the early solar system. It is a place where complex physical and chemical processes continue, where there are layers and boundaries and possibly interfaces between solid, liquid, and gas. It is, in a sense, still evolving, still changing, though on timescales that make human history seem like a moment. The existence of a subsurface ocean would also help explain Pluto's geological activity. Liquid water is less dense than ice, so as the ocean slowly freezes from below, the expanding ice could crack the surface, creating the complex fracture patterns visible in some regions. And the heat released by freezing could drive the convection observed in Sputnik Planitia. Everything connects, each observation supporting and reinforcing the others, building a coherent picture of a world far more intricate than we imagined. Pluto does not travel alone through the outer solar system. It is accompanied by 5 known moons, the largest of which is Charon, over half Pluto's diameter and massive enough that the two bodies orbit a common center of gravity that lies between them rather than inside Pluto. Charon is often described as Pluto's binary partner rather than simply its moon. The two are locked in synchronous rotation, always showing the same face to each other, frozen in a gravitational embrace that will last as long as the solar system exists. New Horizons captured detailed images of Charon as well, revealing another world of surprises. Charon's surface is dominated by water ice, harder and more durable than Pluto's volatile ices. Much of Charon is ancient and heavily cratered, recording billions of years of impacts. But there is also a younger terrain, a smooth plain near the equator that suggests relatively recent resurfacing. And most strikingly, Charon's North Polar region is stained a distinctive reddish color, a feature that has come to be called Mordor macula, after the dark land in Tolkien's fiction. The origin of this red color puzzled scientists at first. Charon has no significant atmosphere of its own, so tholins cannot form in the same way they do on Pluto. The answer appears to lie in a slow, subtle transfer of material from Pluto to Charon. Over millions of years, some of the methane molecules in Pluto's atmosphere escape into space. A fraction of these molecules are captured by Charon's weak gravity and settle onto its surface, particularly near the poles where the coldest temperatures allow methane to stick. Once on the surface, these methane molecules are exposed to the same ultraviolet radiation and energetic particles that create tholins in Pluto's atmosphere. Slowly, The methane is processed into more complex hydrocarbons, which accumulate as a dark, reddish residue. This process is extremely slow, building up a thin coating over millions of years. But time is abundant here, and the red stain on Charon's pole is the visible result of patient, incremental chemistry. In a sense, Charon's red pole is a shadow of Pluto's atmosphere, a marker of the slow leak of gases from one world and their eventual accumulation on another. It is a reminder that even in the near vacuum of the outer solar system, there is exchange and interaction. Nothing is truly isolated. Even worlds separated by thousands of miles influence each other, though the timescales involved are so long that we can only perceive them through the accumulated evidence left behind. Looking at Charon, we see not just a moon but a recorder of history, a surface that remembers events that happened eons ago and preserves them in chemical form. The four smaller moons of Pluto, named Styx, Nix, Kerberos, and Hydra, are tiny compared to Charon, ranging from about 10 to 30 miles across. New Horizons was able to capture images of these moons, though not in as much detail as Pluto and Charon. What the images revealed were irregularly shaped bodies, likely fragments from an ancient collision that may have formed Charon itself. These small moons tumble chaotically in their orbits, their rotation states apparently unstable due to the complex gravitational interactions between Pluto, Charon, and each other. They are bright, reflecting sunlight efficiently, which suggests their surfaces are relatively clean water ice. They are also very low in density, possibly porous or loosely consolidated rather than solid chunks of ice. These are the smallest members of the Pluto system, minor players in the grand dance, but they add to the overall sense of this region as a complex multi-body system rather than a simple planet and moon. Each of these tiny worlds has its own story, its own history of formation and evolution, and each contributes in a small way to the dynamics of the system as a whole. Gravitational interactions between the moons and the transfer of angular momentum over time have shaped their orbits and will continue to do so for billions of years to come. They are part of the fabric of this place, threads in the larger pattern. After the Pluto flyby, New Horizons did not shut down. The spacecraft was still healthy, and it was traveling deeper into the Kuiper Belt, a region of space beyond Neptune's orbit where thousands of icy bodies orbit the Sun in relative isolation. This is the realm of the small, the cold, and the ancient. The objects here have been in deep freeze since the solar system's formation, preserving materials and conditions from that earliest era. Mission planners began searching for another target, another Kuiper Belt object that New Horizons could visit. The challenge was finding something within the spacecraft's reach given its trajectory and remaining fuel. After an extensive survey using telescopes on Earth and in space, they identified a suitable target, an object initially known by the catalog designation 2014 MU69, later officially named Arrokoth. Arrokoth orbited the Sun at a distance of about 4 billion miles, even farther out than Pluto. It was small, perhaps 20 miles long, and incredibly faint, reflecting so little sunlight that it was barely detectable even with powerful telescopes. But it was reachable, and so New Horizons adjusted its course slightly, using a small amount of fuel to set up an encounter that would occur on New Year's Day 2019. The spacecraft once again entered a long coast phase, traveling through the vast emptiness of the Kuiper Belt, heading toward a world no one had ever seen. The journey from Pluto to Arrokoth took 3.5 years. During this time, New Horizons traveled over 1 billion miles, moving through a region of space where the Sun is reduced to a bright star, no longer a disk but a point of light that offers little warmth. The spacecraft operated on battery power generated by a radioisotope thermoelectric generator, a device that converts heat from the decay of plutonium-238 into electricity. This power source slowly weakens over time as the radioactive material decays, but it is reliable and requires no sunlight, making it ideal for missions to the outer solar system where solar panels would be ineffective. New Horizons spent most of this time in hibernation again, waking periodically to check its systems and transmit status reports. The Kuiper Belt, despite its name, is mostly empty. The objects here are scattered across enormous distances, and the chance of randomly encountering one is negligibly small. Space is vast, and even in regions we think of as crowded, the emptiness dominates. The spacecraft traveled in silence, a tiny machine carrying human ingenuity into the outer darkness. And on Earth, the mission team continued to prepare, planning the observations for the Arrokoth encounter, refining the flyby sequence, and hoping that the spacecraft would remain healthy enough to complete this extended mission. As 2018 turned to 2019, Arrokoth began to appear in New Horizons cameras, first as a faint point, then slowly resolving into something more. On January 1st, 2019, New Horizons flew past Arrokoth at a distance of just 2,200 miles, closer than it had passed Pluto. The encounter was brief, just a few hours of intensive observation as the spacecraft hurtled past at over 32,000 miles per hour. Then, once again, New Horizons turned away to transmit its findings home. The data took months to arrive, traveling across 4 billion miles at the speed of light. When the first detailed images appeared, they revealed something no one had predicted. Arrokoth was not a single round object. It was two objects, two lobes connected by a narrow neck, giving it the appearance of a cosmic snowman or, in more technical terms, a contact binary. The larger lobe was roughly 12 miles across, the smaller about 9 miles, and they were gently fused together at the point of contact. The surface was smooth and relatively featureless, with only a few small craters. The color was distinctly red, even more so than Pluto's darkest regions, suggesting a surface rich in tholins. And the shape was rounded, almost gentle, with no sharp edges or violent features. This was not the result of a high-speed collision. It was something else entirely. Scientists analyzing the data concluded that Arrokoth formed from two separate bodies that came together very gently, drifting toward each other at walking speed or slower, touching and sticking rather than smashing. This gentle merger was only possible in the calm environment of the early solar system. The significance of Arrokoth's shape extends beyond the object itself. It provides a window into the process of planetary formation in the early solar system. In the traditional model, planets grew through a series of violent collisions, small bodies smashing together and accumulating mass through accretion. But Arrokoth's gentle merger suggests that, at least in the outer solar system, growth may have been more peaceful. Objects drifted together slowly, their gravitational attraction pulling them into contact rather than flinging them together at high speeds. This peaceful accumulation is consistent with theoretical models of how planetesimals formed from the dust and gas of the solar nebula. In the densest regions of the protoplanetary disk, particles began to clump together, forming larger and larger aggregates. These aggregates were loosely bound, held together by gentle gravitational and electrostatic forces. As they grew, they became more tightly bound, eventually forming solid bodies like Arrokoth. The lack of significant craters on Arrokoth also tells us something important. It means that this region of the Kuiper Belt has been relatively quiet for billions of years. If there had been many collisions, the surface would be heavily cratered. Instead, it is smooth, ancient, undisturbed. Arrokoth is a survivor from the earliest days, a pristine sample of what the outer solar system was like when everything was new. It has been waiting here unchanged for 4.5 billion years. The reddish color of Arrokoth's surface is even more intense than on Pluto, suggesting that the tholins here have had billions of years to accumulate without disturbance. Unlike Pluto, Arrokoth has no atmosphere and no active geology. There is no process to renew or replace the surface material. What you see is what has been there since the beginning, slowly modified by radiation and micrometeorite impacts but otherwise unchanged. This makes Arrokoth an invaluable scientific target. By studying its composition and surface properties, scientists can learn about the materials that were present in the outer solar system during planet formation. These are the building blocks from which the giant planets and their moons were assembled. And some of these materials, delivered to the inner solar system by comets and asteroids, may have contributed to the formation of Earth's oceans and possibly even the origin of life. So in a sense, to study Arakoth is to study our own origins. The molecules on its surface may be chemically related to the molecules that became part of Earth billions of years ago. The processes that shaped Arakoth may be the same processes that shaped the early Earth, before life emerged and transformed the planet. Looking at Arakoth, we are looking at a chemical ancestor, a frozen record of the raw materials from which everything else was made. And it is beautiful in its simplicity, its gentle curves and smooth surfaces speaking to a time before complexity, before life, before awareness. The Kuiper Belt extends far beyond Arakoth, stretching outward to perhaps 50 astronomical units from the Sun or more. An astronomical unit is the average distance between Earth and the Sun, about 93 million miles. At 50 astronomical units, the Sun's gravity is still dominant, but it is weakening, and the time it takes to complete an orbit is measured in centuries. The Kuiper Belt is home to thousands of known objects and likely millions of smaller bodies too faint to detect from Earth. These objects range in size from small pebbles to worlds nearly as large as Pluto. They are made primarily of ice, water ice mixed with frozen methane, nitrogen and carbon monoxide, along with rocky material and complex organic compounds. This is the debris left over from the formation of the solar system, material that never coalesced into planets. In the inner solar system, similar leftover material formed the asteroid belt. But out here, where temperatures have always been near absolute zero, the debris is icy rather than rocky. And because it has never been heated or altered significantly, it preserves a chemical record of the solar nebula, the cloud of gas and dust from which the sun and planets formed. Studying the Kuiper Belt is like reading a history book written in ice and rock. Each object is a page containing information about conditions and processes from billions of years ago. Some Kuiper Belt objects have highly elliptical orbits that bring them much closer to the sun at certain times. These objects occasionally enter the inner solar system, where the sun's heat vaporizes their ices, creating the glowing comas and tails we recognize as comets. Every comet you have ever seen began as a Kuiper Belt object or a similar body from the even more distant Oort cloud. They are visitors from the outer darkness, messengers carrying material from the cold regions into the warmth of the inner solar system. When a comet approaches the sun, its ices sublimate, turning directly from solid to gas without becoming liquid. This gas carries away dust and other particles, creating a glowing cloud around the comet's nucleus. Sunlight and the solar wind push this material away from the sun, forming the characteristic tail that can stretch for millions of miles. But the nucleus itself, the solid body at the heart of the comet, is just a Kuiper Belt object temporarily displaced. When the comet's orbit carries it back to the outer solar system, it freezes again, becoming dormant until its next pass near the sun. This cycle has been repeating for billions of years. Some comets have made thousands of passes through the inner solar system. Others are on their first visit, fresh from the Kuiper Belt or the Oort cloud, carrying pristine material that has never been heated. These objects are particularly valuable for study because they represent the most primitive matter available. The vastness of the Kuiper Belt is difficult to comprehend. Even though it contains millions of objects, they are spread across such enormous distances that the region is effectively empty. If you were standing on one Kuiper Belt object, the nearest other object might be millions of miles away, invisible to the naked eye even though space is perfectly clear. You would be surrounded by darkness, with the sun reduced to a bright star that casts almost no warmth. The Milky Way would be clearly visible, a river of light spanning the sky, far more prominent than the distant sun. This is a place where the solar system begins to blend into interstellar space, where the sun's influence fades and the cold and dark of the galaxy take over. And yet, it is still part of our cosmic neighborhood, still bound by the same gravity that holds Earth in its orbit, just much more gently. New Horizons is now traveling through this realm, moving ever deeper into the Kuiper Belt. It has no more planned targets, no more encounters scheduled. It is simply continuing outward, slowly, patiently, transmitting data when it has something to report and otherwise conserving its dwindling power. Eventually, perhaps in the 2030s, the spacecraft's power supply will weaken to the point where it can no longer operate its instruments or communicate with Earth. At that point, New Horizons will fall silent, but it will continue moving outward forever, a small piece of human technology traveling through the cosmos. Some Kuiper Belt objects have highly elliptical orbits that bring them much closer to the Sun at certain times. These objects occasionally enter the inner solar system, where the Sun's heat vaporizes their ices, creating the glowing comas and tails we recognize as comets. Every comet you have ever seen began as a Kuiper Belt object or a similar body from the even more distant Oort cloud. They are visitors from the outer darkness, messengers carrying material from the cold regions into the warmth of the inner solar system. When a comet approaches the Sun, its ices sublimate, turning directly from solid to gas without becoming liquid. This gas carries away dust and other particles, creating a glowing cloud around the comet's nucleus. Sunlight and the solar wind push this material away from the Sun, forming the characteristic tail that can stretch for millions of miles. But the nucleus itself, the solid body at the heart of the comet, is just a Kuiper Belt object temporarily displaced. When the comet's orbit carries it back to the outer solar system, it freezes again, becoming dormant until its next pass near the Sun. This cycle has been repeating for billions of years. Some comets have made thousands of passes through the inner solar system. Others are on their first visit, fresh from the Kuiper Belt or the Oort cloud, carrying pristine material that has never been heated. These objects are particularly valuable for study because they represent the most primitive matter available. Reflecting on the New Horizons mission and its discoveries at Pluto and Arrokoth, we are reminded that our solar system is far more diverse and complex than we once believed. Every world is unique, shaped by its own history and governed by its own processes. Pluto is not like Mars or Mercury or any other world we have visited. It is itself distinct and irreducible, with its own beauty and its own story to tell. The same is true for Charon, for Arrokoth, for every moon and asteroid and comet we have explored. This diversity is humbling. It suggests that even though we have sent spacecraft to every planet and many smaller bodies, we have only scratched the surface of what the solar system contains. There are still thousands of unexplored worlds, each with its own secrets. And beyond our solar system, there are billions of other systems, most of which likely contain worlds we have never imagined. The universe is full of wonders, more than any single civilization could ever catalog or understand. And yet the effort to explore, to observe, to learn is worthwhile precisely because it is inexhaustible. There will always be more to discover. There will always be new horizons, both literal and figurative. The mission that carried that name has shown us that distance is not an insurmountable barrier, that patience and ingenuity can take us anywhere we choose to go, given enough time and enough will. The images from New Horizons have become part of our collective imagination. The heart-shaped region on Pluto is now iconic, recognizable even to people who do not follow space exploration closely. It has appeared in art, in literature, in popular culture. It represents something hopeful, a reminder that even in the coldest, most distant places, there is beauty and structure and meaning. The universe is not hostile or empty. It is full of pattern and order, governed by physical laws that produce outcomes of surprising elegance. The cellular structure of Sputnik Planitia, the haze layers in Pluto's atmosphere, the gentle merger that created Arrokoth, all of these speak to a universe that is comprehensible, where effects follow from causes in ways we can understand and predict. This comprehensibility is perhaps the most profound discovery of all. It means that the universe is knowable, that we can learn its rules and use them to explain what we see. And it means that our place in the universe is not as outsiders but as participants, beings who have emerged from the same processes that shaped the stars and planets, capable of understanding our own origins. To look at Pluto is to look back at the raw materials from which we came. And to send a spacecraft across billions of miles to see it up close is to affirm our ability to transcend our origins, to become something more than passive products of cosmic evolution. The scientific papers that have emerged from the New Horizons data will keep researchers busy for decades. Each image, each spectrum, each measurement contains layers of information that require careful analysis and interpretation. Graduate students are writing dissertations on Pluto's nitrogen cycle, on the formation of Charon, on the composition of Erekatha's surface. Conferences are held where scientists present their latest findings, debate interpretations, and plan follow-up observations using telescopes on Earth and in space. The mission may be over in the sense that the flyby happened years ago, but the science continues. New insights emerge as researchers develop better models, as they compare Pluto to other worlds, as they apply new analytical techniques to the data. This is the long tail of exploration, the patient work of understanding that follows the initial excitement of discovery. And it is just as important as the mission itself. The spacecraft gathered the data, but it is people who extract meaning from it, who connect observations to theories, who build the frameworks that allow us to comprehend what we have seen. In this sense, the mission is not something done by a machine but by a community of scientists, engineers, and support staff working together over years and decades. New Horizons is just the tool they use to reach out and touch a distant world. The real exploration happens in offices and labs and conferences, where data becomes knowledge and knowledge becomes understanding. There are plans, still tentative, for future missions to the outer solar system. Some scientists advocate for an orbiter to Pluto, a spacecraft that would not simply fly past but would stay, observing the world over time, watching how it changes through its long seasons. Such a mission would be enormously challenging, requiring more fuel and more time than New Horizons used. But it would provide a depth of understanding that a flyby cannot match. Others propose missions to Neptune and its large moon Triton, which may be a captured Kuiper Belt object similar to Pluto. Still others want to send spacecraft to more Kuiper Belt objects, building up a catalog of these ancient worlds to better understand the diversity and history of the region. All of these missions remain in the planning stages, dependent on funding and competing with other priorities. But the fact that they are being discussed at all is a testament to the success of New Horizons. The mission showed that the outer solar system is accessible, that we can send spacecraft there and get back data that transforms our understanding. And it showed that the destinations are worth visiting, that they hold surprises and beauty that justify the effort and expense. Whether any of these future missions will be approved and built remains to be seen. But the desire is there, the vision of continuing to explore, to push our reach farther and farther into the cosmos. One of the quiet lessons of the New Horizons mission is the value of patience. The spacecraft took nearly a decade to reach Pluto, traveling at speeds that pushed the boundaries of what our technology could achieve. And still, it was not fast enough. The universe operates on timescales that dwarf human lifetimes. Light itself, the fastest thing in existence, takes over 4 hours to travel from the Sun to Pluto. Radio signals from New Horizons, also traveling at light speed, took the same time to reach Earth. Everything about the mission required waiting. Waiting for the launch window. Waiting for the spacecraft to reach Jupiter, then to reach Pluto. Waiting for the data to trickle back across the solar system. And then waiting again as scientists analyzed the data, wrote papers, refined their understanding. This patience is not passive. It is active, purposeful, a recognition that some things cannot be rushed. You cannot make a spacecraft travel faster than physics allows. You cannot make light move more quickly. You cannot compress the process of scientific understanding into an instant. The rewards of exploration come to those who are willing to wait, to commit to projects that will take years or decades to complete, and to trust that the eventual payoff will justify the time invested. In our culture, which often prioritizes speed and instant gratification, the New Horizons mission stands as a counterexample, a reminder that the most meaningful achievements require sustained effort over long periods. The engineers and scientists who designed and built New Horizons knew when they started that some of them might not live to see the flyby. The mission was approved in 2001, and the encounter did not happen until 2015, 14 years later. Some members of the team retired, some moved on to other projects, and some passed away, their contributions to the mission complete, but their personal journey ended before they could witness the outcome. This is the nature of long-term projects. They span generations, or at least significant portions of careers. The people who built the spacecraft were not the same people who operated it during the flyby. Different skills were needed at different stages, and the team evolved to meet those needs. But there was continuity as well. Mission Principal Investigator Alan Stern remained with the project from its inception through the encounter and beyond, providing vision and leadership throughout. Many other key personnel stayed with the mission for years, becoming deeply invested in its success. For them, the flyby was not just a scientific event but a personal milestone, the culmination of a significant portion of their professional lives. And when the first images arrived and they saw Pluto in detail for the first time, the emotion was palpable. There were tears, cheers, celebrations. Not just because the science was exciting, though it was, but because the moment represented the fulfillment of a shared dream. In the images from New Horizons, we see Pluto as it was in July 2015, frozen in that moment by the camera. But Pluto itself continues to change, slowly, imperceptibly. The nitrogen ice in Sputnik Planitia continues to convect. The atmosphere continues to evolve as Pluto moves along its orbit. Tholins continue to settle onto the surface, gradually altering its color. The subsurface ocean, if it exists, continues to slowly freeze or perhaps to remain stable, depending on the balance of heat sources and losses. These changes happen so slowly that they would not be visible even if we could watch continuously for decades. But they are happening nonetheless. Pluto is not a static photograph. It is a living system in the broadest sense of that term, a place where processes continue, where energy flows, where the state of the system evolves over time. If we could return to Pluto 1 million years from now, we might see subtle differences. Some craters might have been erased by resurfacing. The pattern of cells in Sputnik Planitia might have reorganized. The atmosphere might be thicker or thinner depending on Pluto's orbital position, but these changes would be minor. The fundamental character of the world would remain the same. This combination of change and stability is characteristic of all worlds. They evolve, but slowly, on geological timescales that make human history seem like a blink. And this is reassuring in a way, a reminder that the universe is not chaotic but ordered, that there is continuity and pattern underlying the apparent flux. Consider what it means that we have seen Pluto. For most of human history, the outer solar system was completely unknown. People could see the stars, the moon, the sun, the planets visible to the naked eye, but nothing beyond Saturn. The concept of Pluto did not exist. The space it occupies was simply empty darkness, part of the undifferentiated night sky. Then telescopes were invented, and gradually, over centuries, we discovered Uranus, Neptune, and finally Pluto. But these discoveries were abstract. Pluto was a point of light, an entry in a catalog, a mathematical prediction confirmed by observation. It was not a place. New Horizons changed that. Pluto became a world, a landscape, a specific location with features you could name and recognize. It gained a kind of reality that it did not have before. And this is what exploration does. It transforms abstractions into experiences, concepts into places. Mars was once just a reddish star. Now it is a planet we have walked on, photographed, studied in detail. The moon was once a mysterious light in the sky. Now we know the names of its mountains and craters, have stood on its surface, brought pieces of it back to Earth. And Pluto, once the faintest and most distant planet, is now a world with a heart-shaped glacier and mountains of water ice. This transformation is irreversible. We cannot unsee what we have seen, and each new discovery makes the universe a little less mysterious, a little more comprehensible. But even as we answer old questions, new ones emerge. The New Horizons data revealed Pluto's complexity, but that complexity raises further questions. How exactly does the nitrogen cycle work? What drives the convection in Sputnik Planitia? What is the nature of the subsurface ocean, if it exists? How did Pluto and Charon form? What is the composition of the dark material in the equatorial regions? Each answer leads to new inquiries, and this is the nature of science. It is not a process that reaches a final destination, but one that continually expands, opening new frontiers even as it closes old ones. This can be frustrating for those who want definitive answers, who want to know everything and move on. But it is also exhilarating for those who understand that the joy is in the exploration itself, not in reaching a final endpoint that does not exist. The universe is inexhaustible. We will never know everything, but we can continue to learn, to refine our understanding, to push the boundaries of knowledge a little farther with each generation. And perhaps this is enough. Perhaps the goal is not to finish but to continue, to sustain the process of discovery as a kind of ongoing conversation with the cosmos. We ask questions, nature responds, and we ask new questions based on those responses. The conversation has no end, but each exchange is valuable in itself. There may be objects in the outer solar system much larger than any we have yet discovered. Some theoretical models predict the existence of a planet-sized body, sometimes called Planet 9 or Planet X, orbiting far beyond Neptune. This hypothetical planet has not been observed directly, but its existence has been inferred from the unusual orbits of some extreme trans-Neptunian objects. Their orbital alignments and inclinations seem to require the gravitational influence of a massive, distant body. If this planet exists, it would be several times more massive than Earth, orbiting at hundreds of astronomical units from the Sun, taking tens of thousands of years to complete a single orbit. It would be extremely faint, reflecting so little sunlight that detecting it would require sensitive instruments and dedicated searches. Several teams of astronomers are currently looking for this object, surveying the sky in the regions where models suggest it might be located. As of now, the search has not been successful, and the existence of Planet 9 remains speculative. But the possibility is tantalizing. If such a world is out there, it would reshape our understanding of the solar system's architecture and history. And if we do find it, there will inevitably be calls for a mission, another spacecraft sent to explore, to image, to study this remote and mysterious world. The story would repeat, another chapter in humanity's ongoing effort to map the cosmic neighborhood. Looking at the Kuiper Belt as a whole, we can see it as a kind of fossil record of the early solar system. Just as paleontologists study fossils to learn about ancient life on Earth, planetary scientists study Kuiper Belt objects to learn about the conditions and processes that prevailed when the planets were forming. The objects here have been preserved by the cold, changed very little over billions of years. They contain information in their compositions, their structures, their orbits. By studying them, we can reconstruct the history of the solar system, understanding how the giant planets migrated, how the smaller bodies were scattered, how the architecture we see today came to be. This work requires many observations, not just of individual objects but of the population as a whole. Surveys conducted with telescopes on Earth have cataloged thousands of Kuiper Belt objects, measuring their orbits, estimating their sizes, and sometimes determining their colors and compositions. This statistical approach complements the detailed studies provided by missions like New Horizons. Together, they build a comprehensive picture. Some Kuiper Belt objects are in nearly circular orbits, moving in lockstep with Neptune due to gravitational resonances. Others have highly elliptical orbits that suggest they were scattered outward by interactions with the giant planets. Still others occupy a more distant region beyond the main Kuiper Belt, a realm we are only beginning to explore. The beauty of the outer solar system is different from the beauty of Earth or even Mars. It is austere, minimalist, defined by subtlety and simplicity rather than lushness and complexity. There are no forests or oceans in the traditional sense, no weather systems churning across blue skies. Instead, there is ice, pale and reflective, marked by gentle shadows and smooth curves. There are colors, but they are muted, earth tones and pastels rather than vibrant primaries. And there is stillness, a sense of time frozen, of change happening so slowly that it is almost imperceptible. This aesthetic appeals to something deep in the human psyche. It is the beauty of winter, of high mountains, of deserts and tundra. It is the beauty of silence and emptiness, of spaces where the distractions fall away and you are left with essentials. To look at images of Pluto is to be reminded that beauty does not require life or motion or warmth. It can exist in the cold and the dark, in the simple geometry of ice formations, in the subtle gradations of color across a frozen plain. And perhaps this realization expands our capacity for appreciation. If we can see beauty in a world as remote and inhospitable as Pluto, then we can find it anywhere, even in places that seem at first glance barren or forbidding. The universe is full of such places, and they all have their own character, their own appeal, their own contribution to the overall richness of existence. The New Horizons mission also reminds us of the importance of basic scientific research. The mission was not designed to solve a specific practical problem or to generate immediate economic benefits. It was purely exploratory, driven by curiosity and the desire to understand. Some people question the value of such missions, arguing that resources should be focused on more immediate concerns. But this perspective misses something essential. The knowledge we gain from exploration, even when it has no obvious application, enriches us. It expands our worldview, challenges our assumptions, and sometimes leads to unexpected insights that do have practical value. Many technologies we take for granted were developed for space missions. The miniaturization of electronics, advances in solar power, improvements in telecommunications, all of these have roots in the space program. And beyond the technological spin-offs, there is the less tangible but equally important benefit of inspiration. Missions like New Horizons capture the public imagination, remind people that humans are capable of extraordinary things, and inspire young people to pursue careers in science and engineering. This inspiration is hard to quantify, but it is real. How many engineers and scientists trace their passion back to a moment when they saw an image from space and realized that exploration was possible? How many innovations have resulted from that inspiration? The chain of causation is complex and indirect, but it is there, connecting curiosity-driven exploration to tangible benefits. As New Horizons continues its journey outward, it is gradually moving beyond the region where the sun's light dominates. Eventually, it will enter the space between stars, where the solar system's influence fades and the galaxy takes over. This transition is not abrupt. There is no clear boundary where the solar system ends. Instead, there is a gradual thinning of material, a slow fade as the density of particles from the solar wind decreases and the density of the interstellar medium increases. The Voyager spacecraft, launched decades before New Horizons, have already crossed this transition and are now in interstellar space, sending back data about the conditions there. New Horizons will eventually do the same, though its trajectory is different, and it will sample a different part of the boundary. This is exploration of a different kind, not of worlds but of environments, not of surfaces but of the properties of space itself. What is the density of the interstellar medium? What is its composition? How does it vary from place to place? These questions may seem abstract, but they are important for understanding the galaxy as a whole. The space between stars is not empty. It contains gas and dust, magnetic fields, and cosmic rays. These components interact with each other and with the material ejected from stars, creating a dynamic, evolving medium that shapes the formation of new stars and planets. By studying this medium directly, we learn about the processes that govern the life cycle of matter in the galaxy. There is a poetic quality to the idea of new horizons traveling forever through space, a small artifact of human civilization carrying our knowledge and curiosity into the cosmos. It will outlast the civilization that built it, still moving long after the last human has lived and died, assuming no other civilization finds and preserves it. It is a message in a bottle, thrown into an ocean far vaster than any on Earth. The golden record it carries contains images, sounds, and information about Earth and humanity, encoded in a way that is intended to be decipherable by any intelligent being. Whether anyone will ever find it, or whether it will drift for eternity unseen, is unknowable. But the act of sending it matters. It represents a gesture of openness, a statement that we are here, that we have wondered about the universe, and that we would welcome contact with others who share that curiosity. In a sense, every space mission is a message of this kind, a declaration that we are a species that looks outward, that seeks to understand and connect. And even if we are alone, even if no other intelligence exists to receive our messages, the effort itself has value. It defines us. It expresses something essential about what it means to be human. We are not content to simply exist. We want to understand, to explore, to reach beyond the boundaries of the known. The data from New Horizons has also contributed to our understanding of how planets and moons remain geologically active. For decades, scientists assumed that small worlds cooled quickly and became geologically dead within a billion years or so of their formation. Larger worlds, with more internal heat, could stay active longer. This principle seemed to explain why Earth is dynamic with plate tectonics and volcanism, while the Moon is largely dead. But discoveries in recent decades have challenged this simple picture. We have found geological activity on small moons like Enceladus and Europa, where tidal heating from their parent planets keeps the interiors warm. And we have found activity on worlds like Pluto, which lack tidal heating and should, by conventional reasoning, be frozen solid. The explanation appears to involve a combination of factors: residual heat from formation, heat from radioactive decay, the insulating properties of thick ice shells, and possibly chemical processes that release energy. The details are still being worked out, but the lesson is clear. We cannot assume that small or distant worlds are inactive. Each world must be evaluated on its own terms, with observations guiding our understanding rather than preconceived notions. This humility is essential for good science. Nature is more creative than we are, more capable of surprising us with unexpected phenomena. The images of Pluto have also found their way into art and culture, inspiring creators across different media. Musicians have composed pieces inspired by the New Horizons mission. Writers have used Pluto as a setting for stories. Visual artists have created works based on the landscapes revealed by the spacecraft. This crossover between science and art is important. It demonstrates that the two domains are not separate but deeply connected. Both involve observation, interpretation, and the search for meaning. Both require creativity and the willingness to see the world in new ways. And both contribute to the richness of human experience. When an artist looks at an image from Pluto and sees beauty, they are responding to the same patterns and structures that scientists find fascinating for intellectual reasons. The aesthetic and the analytical are two ways of engaging with the same reality, and both are valid. By bringing them together, we deepen our connection to the universe. We see it not just as a collection of facts to be cataloged, but as a source of wonder, mystery, and inspiration. And this holistic engagement is perhaps the most profound outcome of exploration. It reminds us that we are not outside observers of the universe but participants in it, beings who are shaped by it and who, in our small way, shape it in return through the act of understanding. In the years since the Pluto flyby, our technology has continued to advance. New telescopes, both on Earth and in space, are being built that will allow us to observe distant worlds in greater detail. Future space missions are being planned that will explore other parts of the solar system. And theoretical models are becoming more sophisticated, allowing scientists to simulate complex processes and make predictions that can be tested against observations. All of this progress builds on the foundation laid by missions like New Horizons. Each discovery informs the next. Each dataset provides context for future observations. Science is cumulative, a collaborative effort that spans generations and institutions. And the progress, while sometimes slow, is real. We understand the solar system far better now than we did 50 years ago. We know more about how planets form, how they evolve, and what processes shape their surfaces and atmospheres. We have a richer sense of the diversity of worlds and the commonalities that unite them. And we have pushed the boundaries of exploration farther than ever before, sending spacecraft to every planet and beyond. This is an achievement worth celebrating, a testament to human ingenuity and determination. But it is also a beginning. The solar system is vast, and we have explored only a small fraction of it. The universe beyond the solar system is incomprehensibly large, full of galaxies, stars, and planets we will never visit. Yet the same spirit that sent New Horizons to Pluto can carry us forward, one step at a time, one mission at a time, into the unknown. As we reflect on the New Horizons mission and the worlds it revealed, we might also reflect on our own place in the cosmos. We are beings who emerged from a planet orbiting an ordinary star in an ordinary galaxy. We are made of elements forged in the cores of ancient stars, scattered through space by supernovae, and reassembled into planets and life. We are the universe become aware of itself, matter organized in such a way that it can observe, think, and wonder. This awareness is rare, perhaps unique in our cosmic neighborhood, though we do not know for certain. And it is precious. It allows us to appreciate the beauty of a frozen plain on a distant world, to find meaning in the patterns of ice and rock, to tell stories about what we see and what it might mean. The images from Pluto are data, measurements of light and color and shape. But they are also more than that. They are glimpses of a reality beyond our everyday experience, windows into a realm that operates by the same physical laws but looks utterly different from anything familiar. And by studying that realm, by sending our machines to explore and report back, we expand our horizons, literally and figuratively. We become a little less parochial, a little more aware of the vastness and diversity of the cosmos. And perhaps that awareness changes us, makes us a bit more humble, a bit more curious, a bit more willing to embrace the unknown. And so we come to the end of this story, though the journey itself continues. New Horizons is still out there, moving through the Kuiper Belt at tens of thousands of miles per hour, farther from Earth with each passing second. It has completed its primary mission, but it remains a traveler, a wanderer in the cosmic dark. Pluto still orbits the sun, its heart of ice slowly convecting, its atmosphere gently shifting, its surface recording the passage of time in subtle ways that we will never see unless we return. Charon still bears its red stain, a memory of ancient exchanges with its partner world. Arikoth drifts in its slow orbit, unchanged and unchanging, a relic of the beginning. And the Kuiper Belt stretches on, full of worlds we have not yet seen, stories we have not yet heard. This is a place of stillness and patience, where time moves at its own pace, indifferent to human urgency. There is peace here, in the cold and the dark, in the gentle geometry of frozen plains and the soft glow of distant sunlight. Let that peace settle over you now. Let the vastness and the beauty remind you that there is more to existence than the immediate and the urgent. There are depths to explore, silences to inhabit, wonders to witness. The journey outward is also a journey inward, a discovery of what it means to be aware in a universe so much larger than ourselves. Rest now in that awareness. Let the stars hold you gently as you drift into stillness. The cosmos is patient, and so can you be.